Hello everyone, my name is Chen, and I come from the School of Electronic and Computer Engineering at Peking University. I also work with OPPO Research Institute. Today I will talk about our work titled Adversarial Diffusion Compression for Real-World Image Super Resolution, abbreviated as AdcSR. This is a collaboration with my colleagues from Peking University, the Hong Kong Polytechnic University, and OPPO. All the code and pre-trained models we used in this project are publicly available, and the GitHub link is shown on the slide. Let me define the task first. Real-world image super resolution refers to recovering a high-resolution image from a low-resolution input degraded by unknown and complex processes. The challenge here is twofold. First, the result must stay faithful to the original image. Second, we must enhance visual quality and run the model fast enough for practical deployment, especially on resource-limited edge devices. The baseline we start from is a representative one-step diffusion model called OSEDiff, short for one-step effective diffusion. OSEDiff repurposes the original Stable Diffusion model, which was designed for generating images from text prompts. It keeps most of the structure from Stable Diffusion, including the VA encoder, the denoising unit, and the VAE decoder. The process has three stages. First, the input low-resolution image is encoded into a latent variable using the VA encoder, while a prompt extractor produces a text condition. Second, the latent is passed through a UNet that performs one-step denoising guided by the text condition. Third, the denoised latent is decoded back into the high-resolution image. Although OSEDiff reduces the sampling step number from multiple to 1, it still uses the full diffusion model backbone. The total number of parameters is 1.8 billion, and inference takes around 110 milliseconds per image on an NVIDIA A100 GPU. This is still too slow and too large for real deployment on mobile phones or other edge devices. This brings us to the core idea of our work. Unlike text-to-image generation, where the model needs to create all visual content from scratch, super resolution starts from a real, informative image. We believe that for real-world super resolution, much of the original diffusion structure might be unnecessary. So we made a hypothesis. If the input already contains rich visual content, we can remove some parts of the model and compress others while still maintaining high output quality. Our goal is to shrink the network structure, keep only the essential modules, and end up with a lightweight model that still performs well. Our first contribution is a method we call structural compression. We start by analyzing the OSEDiff pipeline and classifying each module. The first category includes removable modules, such as the VAE encoder, the prompt extractor, and the time embedding. These are removed entirely. The second category includes prunable modules, namely the UNet and the decoder. We reduce the number of channels in the UNet by 25% and in the decoder by 50%. We remove the VAE encoder because it compresses the image by a factor of 48, which causes the loss of structural details important for super resolution. Prompt and time embeddings contribute very little to quality in one-step inference, but consume a lot of parameters, so we eliminate them. After pruning, the remaining network only consists of a UNet and a decoder, both channel reduced. This yields a simple, efficient architecture. However, direct pruning leads to performance loss. To solve this, our second contribution is adversarial distillation. It is a two-stage training scheme. In the first stage, we freeze the encoder and pre-train the pruned decoder using reconstruction loss. This helps the decoder learn to decode from the same latent space as before. In the second stage, we distill knowledge from the large OSEDiff model into our small AdcSR model. We match their intermediate features using L1 loss. Then we add a discriminator to evaluate the realism of the output features. We use a GAN-style loss to encourage the student model to generate realistic features. This entire process happens in feature space, not image space, so it is more efficient. We tested our model on the Real-ISR benchmark, which is widely used for evaluating 4x super resolution. Our model performs well across all major metrics. In LPIPs and DIS, which measure perceptual similarity, we match or beat previous methods. In PSNR and SEM, which reflect pixel-wise accuracy, we are also competitive. Visually, our model recovers clearer feathers, textures, and sharp edges, even though it is much smaller than others. Now let's look at efficiency. This bubble plot shows model size and speed. Our model is in the bottom left corner, meaning it is both fast and light. We deployed AdcSR on a Snapdragon 8 Gen 4 mobile chip. Compared to OSEDiff, our latency dropped by 97%, memory usage by 71%, and model size by 74%. We achieve real-time inference for 4 times super resolution on a real smartphone chip. To summarize, we propose AdcSR, a compressed and distilled super resolution network. We remove redundant modules, prune essential ones, and use adversarial distillation to retain quality. Our final model is 3.7 times faster, 74% smaller, and still delivers state-of-the-art visual results. It is the first one-step diffusion-based super resolution model that runs in real time on edge devices. All of our code, pre-trained weights, and testing demos are open-sourced. You can find them at the GitHub link. If you have questions, please feel free to contact me via GitHub, email, or WeChat. This project was made possible by our collaboration between the Visual Information Intelligent Learning Lab at Peking University, the Hong Kong Polytechnic University, and OPPO Research Institute. Thank you for watching. If you want to learn more, please visit our poster at CVPR. I'll be happy to answer any questions and discuss more details.